In this video we're going to discuss about the isobaric process, which means constant pressure. For instance, if we have once again a PV diagram, in the PV diagram we're going to see once again a straight line, but in this case it's a horizontal line. The work, which is for instance integral of PdV, is going to be the area below the curve, which is for instance P times the change in volume. In this case the first law is once again Q minus W equals change in internal energy, and the work is P delta V, and here it is relevant to define a new quantity, which is the enthalpy. Enthalpy is a combination of properties. It is denoted with the letter H, and it's U, the internal energy, plus PV. We could define it and we could try to understand it. So we can say it's the total energy of the system when we're talking only about the thermal energy being the internal energy, and the energy due to work, PV. Not the total, since we're not taking into account kinetic energy, potential energy, etc. But let's not focus on this. It's just a convenient property or set of combinations or of properties is for convenience, and that is called the enthalpy. It is straightforward to understand that the derivative of the enthalpy equals du plus dPV, which is for instance du plus PdV plus VdP. Now, since we are studying an isobaric process, this term will cancel, VdP. And if we do the integral, we can get that in an isobaric process, delta H equals delta U plus P delta V. So in this case, in an isobaric process, we can redefine the first law by stating that the heat is going to be equal to a change in enthalpy. Enthalpy can come out from tables as well, as usual, when we're talking about water or refrigerant. But talking about other systems, we can define the heat capacity at constant pressure, Cp, as the change in enthalpy with respect to temperature at a constant pressure. Given the situation, the specific heat at constant pressure will give us the change in enthalpy. A change in a specific enthalpy is going to be equal to the integral of Cp dt. Where can we get values of Cp? Well, table A2 gives us values of Cp, but this is at 300 Kelvin. Since Cp is changing with respect to temperature, we can have reported Cp's at various temperatures. For instance, at different temperatures, and this is for different gases: air, carbon dioxide, carbon monoxide, etc. A more complete information is given in this kind of table, where we have Cp. Just take into account that the temperature in this table is with respect to Kelvin, while the Cp is in kilojoule per kilomole Kelvin. So, whenever you do the integral, since delta H specific is the integral of Cp dt, well, you can do the integral of A plus Bt plus Ct to the square plus Ct to the cube dt, etc. Well, the integral is going to be, for instance, AT plus B over 2T squared plus C to T to the cube over 3 plus, and I'm missing D, T to the 4 over 4 evaluated from T1 to T2, and this delta H is going to be given in kilojoule per kilomole. So be aware of this whenever you use this kind of table. So remember, the first law of thermodynamics only right now, only for the isobaric process, is Q equals delta H, and this is not taking into account other kind of work, which is not the P delta V work, okay? So if there is an electric work or whatever, we have to add it.